In the back corridors of Europe's agricultural frontier, something extraordinary happens every week. Convoys cross borders, carrying not grain, not fruit, not tractors, but wild boars. Not the domesticated, docile kind raised in enclosed farms, but true wild specimens born with instinct, muscle, and reaction times that turn transport into a biomechanical puzzle. Each one is a compact storm of power, capable of producing over 200 kilograms of force when it panics. And when hundreds of them are loaded onto a truck, this isn't just a logistical task. It becomes a dynamic physics problem in motion. Transporting them is not a matter of containment. It's a matter of balance, force dispersion, and anticipation. Like naval engineers calculating ballast adjustments in cargo ships to prevent capsizing under wave motion, designers of wild boar transport systems must engineer against a different kind of wave, the collective shift of live, reactive mass. One sudden jolt, one honk, one vibration too sharp, and a peaceful load can turn into synchronized chaos. The crates don't just carry animals, they carry potential energy, stored in muscle, instinct, and fear. That's why traditional containment systems borrowed from pig farming, the ones designed for calm, sedentary livestock, collapse under the conditions of wild boar transport. Their geometry, their flooring, their material memory, all inadequate against the sudden lateral surges of a frightened herd. What works for pigs fails for boars. The species might look similar, but the transport challenge is altogether different. The unpredictability isn't just physical, it's behavioral. Wild boars don't respond uniformly to stress. Some freeze, some charge, some pace endlessly in circles. This inconsistency isn't just a matter of discomfort. It affects loading times, injury rates, and even the interior temperature of the container. An invisible variable, buried in biology, makes logistics exponentially harder. And yet, shipments continue. Borders are crossed. Meat arrives. Somehow, the system works. The solution begins where engineering meets animal behavior. Agro-industrial designers began reshaping the paths boars take from pen to crate, introducing anti-panic funneling geometries, inspired by the curved raceways developed for cattle, but now adapted with spiral segmentations that interrupt line of sight and slow forward momentum. It's not about forcing the animal in. It's about convincing it there's nowhere else to go. Because every corner of this process, from pen to ramp, from truck to border, is governed by force, reaction, and structure. And so the question arises, if freight wagons that carry iron ore are carefully engineered to absorb and redistribute load oscillation, why do we still use rigid, flat-bottomed crates to contain muscular, reactive animals in motion? Maybe it's time to recalibrate. Maybe it's time to treat wild boar transport not as a version of pig logistics, but as a high-stakes experiment in biomechanical containment, a moving system where every bolt, bar, and bracket must be in harmony with instinct itself. Stress doesn't just move bodies, it alters them. In the case of wild boars, the journey begins with a shift that's nearly invisible, hormonal. When the loading phase begins, even before the animals step onto the ramp, the first biochemical markers of deterioration are already in motion. Cortisol, the primary stress hormone, surges through their bloodstream. Muscles tighten, blood vessels constrict, and what was once potential meat begins a silent transformation, not through time or temperature, but through fear. This is not just a question of comfort, it's chemistry. Elevated cortisol levels disrupt the balance of glycogen in the muscles, triggering an early acidification process that lowers pH and accelerates drip loss. The release of vital fluids that affect texture, weight, and shelf life. In scientific terms, the meat begins to spoil before transport even begins. In commercial terms, quality is lost before the product ever reaches its destination. To fight this invisible sabotage, agro-logistics engineers are rethinking the spaces where stress first takes hold. Preloading pens are now being redesigned as behavioral buffering zones. Instead of concrete walls and shouting handlers, exporters are integrating soft visual barriers, curved corrals, and ambient auditory diffusers that mask sharp noises. These aren't luxuries. They are neuromechanical interventions grounded in studies from animal neuroscience that show how even minor environmental changes can stabilize heart rates and reduce cortisol surges within minutes. The number of handlers also matters, not just for operational simplicity, but for biological integrity. Field studies show that wild boars exposed to more than 3 different human handlers during loading exhibit up to 38% more biochemical spoilage markers than those moved by 1 or 2 trained personnel. The implication is profound. Every added human variable increases the animal's stress response, and that stress becomes measurable, edible loss. One exporter in Hungary understood this equation and redesigned the entire pre-loading process. They implemented a single-flow corridor system with noise-dampening panels built directly into the containment structure. The effect was immediate. In just 6 months, the company recorded a 22% reduction in DFD cases, the condition known as dark, firm, and dry meat, a well-known result of pre-mortem stress. The solution didn't require sedation, expensive chemicals, or high-tech tracking systems. It required spatial intelligence and respect for behavioral mechanics. So the question remains, what are we really moving across these borders? Is it simply meat, packed in crates, bound for processing? Or is it something more dynamic, a chain of biochemical reactions in progress, shifting with every sound, scent, and motion? To understand wild boar transport is to accept that stress is not an afterthought. It's a variable, a damaging one. And the battle to preserve quality doesn't start with refrigeration. It starts with silence, shape, and control. The word cage might suggest simplicity, a metal frame, a locking door, a system of barriers. But when applied to the transport of wild boars, this concept collapses under its own assumptions. Traditional cages, designed for the calm cadence of domestic pigs, are ill-equipped for animals that fight movement with instinct and muscle. When boars panic inside these enclosures, the result is not just agitation. It's kinetic force, redirected into bars, walls, and joints that were never engineered for lateral impact. A single charge from a wild boar in transit doesn't simply test the structure. It destabilizes the load, causes adjacent animals to react, and in many cases cracks welds, bends supports, or creates points of escape. Insurance reports from transport routes across Eastern Europe cite repeated injuries, structural failure, and costly interruptions, all traced back to cages unfit for the species they carry. It's not just a design flaw, it's a misreading of behavior as static, when in reality it's dynamic and forceful. This is where new thinking enters the equation. Engineers and logistics specialists began adapting containment technologies from entirely different sectors, namely military field operations. Inspired by transport cages used for high-intensity canine units, a new generation of hybrid modular systems emerged. These aren't mere metal boxes, they are mechanical structures, built with shock-distributing exoskeletons, stress-dispersing corner joints, and composite flooring that eliminates slippage, a critical factor in injury prevention during acceleration and braking. The results are measurable. In comparative tests conducted along curved road segments common in border transport routes, traditional cages experienced a failure rate of 1 in 14 units due to lateral G-forces. In contrast, not a single composite-framed cage failed under the same test conditions. The data doesn't just confirm a design advantage, it reveals a shift in logic, from containment as restriction to containment as adaptation. This shift is already reshaping operations. One Polish logistics firm retrofitted 20% of its livestock transport fleet with these advanced modular systems. The outcome was a 70% reduction in animal injury claims in just 1 fiscal year. Fewer injuries mean lower stress, higher meat quality, and tighter delivery schedules. The crates now serve not only as physical protection, but as logistical stabilizers for an entire supply chain. And behind this success lies a new paradigm. The idea that a transport cage is no longer a passive container, but a responsive mechanical system, one that interprets and absorbs the multidirectional force vectors of living, sentient cargo. Wild boars don't travel like freight. They travel like energy in flux. And the only way to move them without loss is to engineer that flux into every bracket, panel, and weld of the system that carries them. If smart design can move wild boars safely, imagine what it can do elsewhere. Check the pinned comment. You'll get it. Transporting wild animals at industrial scale is one of the most demanding tests modern agriculture can face. It's not only about fuel efficiency, crate capacity, or export deadlines. It's about translating raw, unpredictable biology into a rhythm that matches wheels, roads, and regulations. Wild boar exports in particular, with their combination of mass, muscle, and instinct, have revealed a fundamental truth. Effective logistics today are not linear operations, but adaptive systems. Systems that learn, absorb, and evolve under pressure. What might look like a steel crate on wheels is, in truth, a dynamic biomechanical environment in motion. At 90 kilometers per hour, a trailer becomes a platform of accumulated tension, lateral forces on curves, micro-vibrations from suspension travel, thermal shifts between microclimates, and the constant feedback loop of animal movement. Each bump, each sway, each deceleration introduces new vectors of stress. Traditional approaches, built on restraint and confinement, have proved inadequate in the face of this complexity. Confinement alone is not control. To control means to predict, to mitigate, and above all, to engineer for variability. This is where the world of agricultural mechanics begins to speak the language of aerospace suspension, architectural damping, and intelligent vibration control. One of the clearest cross-industry inspirations comes from the precision systems found in modern smart sprayers, agricultural machines that, despite traversing uneven soil at speed, maintain millimeter-level stability in their nozzles. These machines isolate micro-movements with precision suspension units that cancel out shocks before they reach the application components. The same principle, reinterpreted, now informs the cage-based structures used in high-stress animal transport, not to improve comfort for its own sake, but to preserve the animal's ability to maintain equilibrium during motion, a critical factor in minimizing muscular fatigue, injury, and panic. Some exporters are going further. In Catalonia, one of the continent's leaders in wild boar protein supply, a logistics company partnered with an engineering firm specializing in high-performance automotive suspension. Their goal: to retrofit animal transport trailers with active gyroscopic stabilizers, originally developed for racing vehicles, capable of keeping crate bases level, regardless of road pitch or directional shift. This adaptation didn't just reduce fall injuries and sliding incidents. It improved the behavior of the animals during transport. Boars that traveled with fewer postural adjustments arrived calmer, with more consistent meat quality markers and fewer post-arrival interventions needed at the processing site. This kind of integration, part biomechanics, part machine learning, part field-tested pragmatism, points to a transformation in how we understand logistics in agriculture. We are no longer looking at a sequence of tasks, but at ecosystems of interaction. Animal, crate, trailer, driver, terrain, each element influencing the others in real time. In this view, a crate is not a box. It is a live data point, and each successful journey is an experiment in forces, rhythms, and thresholds. When injury rates drop or cortisol spikes decrease, it isn't just the animal that wins. It's the system proving it can learn. To treat wild boar transport as simply moving livestock is to miss the scale of ingenuity involved. What we are seeing is a convergence between mechanical design, animal behavior analysis, and real-time logistics adaptation. A container that flexes slightly at the right moment, a wall panel that muffles certain frequencies, a floor that responds to sudden shifts in weight like a pressure-sensitive membrane. These are not isolated upgrades. They are components of a holistic redefinition of how agriculture thinks about movement, control, and biological preservation under stress. The lesson is deeper than transport. It reflects a broader principle that modern agribusiness, when it succeeds, does so not by overpowering nature, but by reading it more precisely. The more accurately we interpret stress signals, movement patterns, and behavioral feedback, the more we can design systems that don't just resist failure, but anticipate and reshape it. The true innovation lies not in making animals adapt to machinery, but in refining machines to respect the physics and biology of what they carry. Because every wild boar exported without injury, without loss of quality, and without triggering its innate fear response is not simply a product delivered. It is a blueprint in motion, a case study of synchronization between mass and engineering, a reflection of how far we've come in merging human intelligence with natural instinct, and how much more we can still discover by paying attention to what these moving systems are quietly teaching us. Before you go, don't miss what's waiting in the pinned comment.